So our next speaker is Andres Freund. He's one of the most active and prolific Postgres committers. He was responsible for many big forward-looking features in recent years, such as logical decoding, table access methods, just-in-time compilation, huge performance improvements, like the list goes on. So he's one of the world's experts on low-level Postgres performance. And he's going to share what kind of tools he uses to analyze performance issues in Postgres. So Andres, take it away.
What you might notice based on the screen is that I might be an expert in low-level performance issues, but I'm not an expert in graphics. So bear with me. I've been doing work on Postgres and around Postgres for 15 years or something. And during a lot of that, I've also tried to solve performance issues for with users or in real-world scenarios. And over the years, I've observed that a lot of people think that some of the tools that might be more developer-oriented can't be used in a more administrative way. So I want to talk today about two of the most interesting tools in the space for investigations on that I know of on Linux, and hope to provide a bit of an intro to get you to get your own start. The first of these tools is Perf, which is a profiling tool that exists in Linux for since I think the 2.6 days. So most, hopefully all the Linux versions that you're going to use Postgres on will have it available. One thing that will be problematic for some of you is that it requires elevated privileges. In the default configuration, it will require you to have root rights. And obviously that will exclude some of you because you are going to run Postgres in some managed environment and you don't have the necessary permissions to do that. But for those of you that do have the permissions, I'm going to try to give you an introduction based on an example of how to get started. I listed occasionally I have a few links for more details for you to get started, because I will only have a few basic examples here, and I'm trying to show my methodology of how to look at performance problems. Let's assume, and this is based on a real-world scenario, that we have a workload, and that workload is surprisingly slow. And it's slower the more connections there are. And we want to know why, because that is not good for fairly obvious reasons. The first thing to do is to run perf on the machine in a system-wide mode. And that is what the -a flag here does. That says run perf and profile all the CPUs, all the processes in the system. And in this case, we do that with sleep3, which will just run the sleep binary for 3 and will return after 3 seconds. And this will collect the data, and then we can look at the data. What I'm doing here is to say that I want to have only the com, and that is the command, and the DSO, that's the shared object that the code that is showing being expensive to execute. And what you can see here is that once you enter this, you will see a prompt that will look something like this. Obviously, which programs and so on are slow will be different in your case. And in the problematic case that we were looking at, we saw that a lot of the time was spent in pgbench. Pgbench is a benchmarking program. In the real scenario, it was actually a different program, but that was my reproduction of the problem. And what is very interesting here is that it's not actually the time spent inside the pgbench tool itself, but what we can see is that the shared object that it's reporting is the kernel. So we know that like more than 70% of the time on the system is spent in the kernel. And even though we're running the benchmark tool and on the same machine as Postgres, Postgres is not using as much CPU as a benchmarking tool. So clearly something is wrong. That is already a pretty good starting point. But because we know that pgbench is the main problem, we can now just look at a profile of just pgbench, because we don't need to have all the other parts of the system. And that we can do by specifying the process, p and the process ID. And this time we just do it for 1 second. It is good enough. That's good enough. And we again do perf report. What you can see here that the time is nearly all spent in the kernel. Like we can see that based on the shared object and on the symbol. And this is already like telling us, oh, that was not intentional. You can already see that it's already somewhere in locking code in the kernel. So something is clearly not quite right, because we shouldn't, the benchmarking tool shouldn't end up causing that much locking. The next step is to see what is calling all that locking function. And you don't really need to know in detail what exactly is those locking functions are. You can just often guess what is happening by, there's one function that is using a lot of CPU. That is probably something wrong. And if it has locking in the name, for example, then you could just guess that that might be a problem and that you should perhaps look at what is causing all those locks. And the way to do that with perf, to look at what the callers are, we can specify that we want to collect the call graph while we are profiling. And that makes the profiles bigger, because it will now collect information about the call stack leading up to a function being called that is expensive. And then once we've done that, we again look at the result. And note that I'm specifying the -- no children option here. And that means that we want to see the expensive function at the top, rather than looking at it the other way around from like the top, like seeing which function, including its children, is expensive. And then one can navigate in the interface, like just with the keys and enter or plus to unfold different menu options, or like the different functions. And what you can see is that once we've gotten through here, is that at some point, a few frames up in the call stack, we can see that like it is something with crypto, and it is something with TLS that is causing all this contention. So what we're dealing with is that somehow the SSL encryption or TLS encryption is causing the performance problem. And with that, the next thing to do would be to search for whether there's anything known about performance problems with locking and TLS. And Postgres, as you might know or might not know, uses OpenSSL. So we can just search for OpenSSL and locking and threads. And the first hit will, in this case, show you, like, lead you to a blog post from the OpenSSL project about threads. That might be a good bit of information. And then we can see here within the first sentence that it was drastically changed in the 1.1 release. And as it turns out, in the real world scenario that we were looking at, we were not yet using 1.1. It was 1.0.2. So a good next step would be to compare whether using a different version of SSL, OpenSSL, improves the problem. And not that it's really important for this case, but just collected the numbers. And when we were using a 1.0 version, we went up to only 10,000 TPS. In this case, it was read-only transactions, but it does not really matter. The important part is just that once we upgraded to something newer, the number of transactions went up by a factor of 4. And at the same time, the CPU usage of pgbench halved. So this is just an example of how when we can go from looking at the top by seeing which processes and in which part of the processes the execution time is in, to then go and know where to look from there. And another simple or trick that can sometimes help when looking at Postgres workloads is to just do the same thing that we did system-wide with --sort com and DSO to look at a single Postgres backend. And what we see here is that 83% of the time is spent in Postgres. That is pretty unsurprising because we are, after all, executing Postgres. But what is interesting is that we can here see all the extensions that Postgres is using separately. And if it is not uncommon that you actually can end up seeing that most of the time is not spent in Postgres itself, but in some extension. For example, if you use PostGIS, it's so often you will see that most of the time is not spent in Postgres code proper, but in the extension code. Or if you have very heavy use of PLPG SQL, you might see that most of the time is actually spent in PLPG SQL instead of Postgres. And that then will give you a good next thing to look at in a bit more detail. I think this might already provide you with enough information to how to do your own first few investigations. Because of that, I want to go and talk about the second tool that I find very useful for investigating performance problems, and that is a tool called bpftrace. BPF is BPF stands for the Berkeley packet filter, and that's just the heritage. It does not actually have anything to do with packet filtering anymore. It can be used for that, but it's a much wider much more widely used, and there's a lot of different tools for using what it can be used for. In our case, we want to use it for tracing, not for packet filtering or any user space networking or anything like that. What bpftrace allows is to define actions that are attached to kernel or user space trace points, and trace points are things that are defined in the source code that are interesting, and so the developer of the software decided that to expose those. It can also do dynamic function probes, and that means that to perform an action when some code is executed, even if the writer of the software didn't intend for that part of the code to be used for tracing. There's also other things we can attach actions to. And when I say actions, the action is basically some C-like code, and that C-like code can collect data, and it can output data. And it's important to note that these actions are executed in kernel space, not in your application or something like that. But they are sandboxed. It's not necessarily, it's a pretty good sandbox, but it's not necessarily perfect. And because of that, it's again limited to root. For those for later viewing, I've included a number of links here to information about bpftrace and about the various scripts I'm using in the next few slides. To just look at an example of what we can collect with bpftrace, one thing that is often interesting to collect, and that is very hard to do with Postgres, and we actually heard Andy Pavlo mention this 20 minutes ago, is that Postgres, when it reads data, it does not just have its own buffer cache, but it also uses the operating system buffer cache. And that means that the statistics in Postgres that show whether we did a read from the operating system does not necessarily translate to read from disk. So what we might want to do is to know which of the reads were actually hitting disk and which not. So I mentioned earlier that we can attach actions to various points. And this is a user space trace point. And this here is a reference to the Postgres binary passed as an argument. And then this is the trace point that Postgres calls whenever a read starts. And what we just do in that case is to set, this is like the add syntax always references a map. And this can be, it's like an associative map, a hash. And the argument that we're, like the key that we're using is the TID, that's the thread ID, and we're just setting 1. And then we have a second trace point that is just whenever the read is done. And we have additionally a condition here that says we are in a read. And what that just does is to handle the case that we might have started tracing while reads were ongoing. And the part where we then now can use actually collect more information than we could get from Postgres statistics alone is that we can also use a kernel trace point. And this call is basically what the kernel calls to read data that we will actually need from disk. And because we don't want to trace the entire system, we just want to trace it when Postgres is doing a read. We have as a condition here that we are currently in a read. And what you then just do as the action is to say, we want to count all the cache misses, and we want to sum up how many bytes were read as part of a cache miss. I also mentioned that we can specify a few other things to attach actions to, and one of those is that we can specify intervals at which we want to do something. So here we say every 1 second, we just print the statistics about cache misses and how many bytes those were, and then we clear them so it next second we start out from have a fresh start. And here there's another point to where we can attach an action to is just the end of tracing, and here we just clear out that array that said like whether the current thread is doing a read. And what that will end up with providing you with is that every 1 second we'll print out how many cache misses there were and how many bytes we were missing. And it'll just loop keep on going until it's done. And if nothing's happening, it'll just say that there's 0 cache misses, or there's more. Like, if there's more, there's more. The next trick is that we can not just collect information globally, we can also say we will do it per process. And so we just collect it in a map with the PID as a key. And then the information will be collected on a process basis. And that works for basically, that's a generic trick. If you want to write scripts like this yourself, it can be useful to know, to see which trace points there are. And for that, you can use bpftrace with the -l argument, and you can either give a name or you can use wildcards to see, get all the matching trace points. For kernel trace points, when you specify -v, it will also tell you about which arguments are defined to the trace points. A very nice additional trick that you can do with this is that bpftrace or bpf tooling for tracing can collect stacks. And what we're doing here is to say that whenever we are waiting for an LW lock, and an LW lock is Postgres' the fast in-memory lock that we're using for things like page locking and so on. And we want to trace how much time are we spending actually in waiting for such locks. So we had one trace point that I'm not showing out of space reasons that was at when begin, and then another one when done. And what we do is just check how much time has passed since the waiting has started, and then we collect the stack, the amount of time, the sum of all the deltas for the current user space stack. And that you can watch that interactively just as a text, or you can convert it to a flame graph, and that is a lot easier to view. And then with just a few lines, you can get a graph like this that will, if you open it in a browser, you can actually click around interactively, show that we were, for example, spending a lot of time vacuuming while we were in index accesses, and a lot of that was actually determining the amount of time it was whether a transaction committed or not. That can be sometimes useful from a developer perspective, but also sometimes from a system administrator perspective, because it can tell you that you might need to change configuration. One very useful thing is that we can associate all this information with pgstat statements. Pgstat statements is a Postgres extension that collects information about each query, and it already has information about how long did the query take, how many times did we hit a buffer, how did we find the data in shared buffers, and how many times did we find it had to go to the operating system. But it does not currently track, for example, whether we hit the kernel cache, and that makes it harder to tune shared buffers. It does not know whether the query was slow because of a lot of data was sent to the client, because, for example, it was collecting all, outputting the whole database in one query. With the tooling with BPF, with bpftrace, we can actually collect all this information by just using another probe when, as part of when pgstat statements store statistics, we can collect additional statistics. For example, in this case, I'm collecting data that is about the data that was sent out over the network, and just this is how that data was collected. It's not that interesting. I will have the link to the scripts. And with all this information, we can then actually collect query pgstat statements with our extra data, and suddenly we know that how to collect data about actual disk reads and how many times we had to shared buffers. And what you can see is, for example, we had to go to in this query, we were going to shared buffers we were missing shared buffers a lot, but most of the data was then actually cached in the operating system, so it was not actually that bad. Cool. With that, I'm basically at the end. I included the link to the slides, and the slides have the links to the bpftrace scripts I had.
All right, thank you very much, Andres. One question is like, how much overhead do the BPF traces have, and could they be used in like production to provide better statistics?
Yes, it's a very good question. I should have probably had some numbers, but it was hard to fit into the time. It is a question of how often you hit the probes. For example, the LW-log weight stats do not measurably seem to have an overhead, because once you already hit a kernel weight, like the probe has no meaningful overhead. If you were to probe like the number of times we were acquiring a log when we're not blocking, then that starts to become very noticeable. So it really depends on the frequency of how often you hit the various probes.
Right. And are there any plans, or do you have thoughts on like what would be useful to include in Postgres or in an extension?
I'm kind of hoping to give people ideas to work around this, but I do think it would be good to have an extension. I don't know whether it would be best done as an in-core extension or just as a dedicated Linux-specific project. I do think that we could make it as part of core Postgres a bit easier to collect some of the information and to associate it, for example, with pgstat statements. There's currently some things that make it a bit harder than it has to be.
Got it. Right. Okay. Thank you very much. We're going to move on to the next speaker.